Hello viewers, in our previous series of sessions we had discussed about carboxylic acids. Today we are going to start another series of sessions where we will discuss carboxylic acid derivatives. In this series today we will discuss that what are these carboxylic acid derivatives, how they are named. We will discuss the IUPAC nomenclature as well as the common nomenclature for acid chlorides, amides, esters and acid anhydrides. Then we shall talk about the physical properties of these acid derivatives. Then these acid derivatives undergo a particular reactions, we call them as nucleophilic acyl substitution reactions. So we shall discuss that why these reactions are named so, and then on the basis of these reactions what is the reactivity order of different acid derivatives that ultimately leads to their stability, and finally we will summarize our today's work. What are these acid derivatives? This formula indicates a carboxylic acid. This COOH group is the functional group, carboxyl group. In different carboxylic acids, this R group can be alkyl group, it can be an aryl group, or it can be an unsaturated carbon chain. We had discussed earlier different types of carboxylic acids. Now when this OH group of this carboxylic acid, it is substituted by some other group, then we get a series of compounds, we call them as carboxylic acid derivatives. When this OH is substituted by chlorine, we get a group of compounds, we call them as acid chlorides, are generally called as acyl chloride. This chlorine is the group that has displaced OH here. In general, we can get a class of compounds called acyl halides, where we can have bromine or iodine also in place of chlorine, but most commonly compounds which are used as well as obtained are acid chlorides. Then when this OH is substituted by NH2 group, that is the amine group from ammonia, the compounds are called amides. When this group is substituted by some alcohol, we get the group of compounds called esters, and when this group is substituted by another acid molecule, we get the group of compounds which are called acid anhydrides. So these four group of compounds, acid chlorides, amides, esters and acid anhydrides, they constitutes carboxylic acid derivatives. Let us discuss the nomenclature system for all of these one by one. First we will take acid chlorides. The acid chlorides are named in IUPAC system as well as by common system, in which ic acid, the suffix in the name of the acid, ic acid, it is replaced by another suffix called acyl chloride. Such as this is the common acid called acetic acid. So common name for this acid is acetic acid, whereas IUPAC name for this acid is ethanoic acid. When OH group of this acid is replaced by Cl, we get this compound CH3COCl. In common system, it is named as, by replacing this ic by yl and then adding chloride, we call it as acetyl chloride. Similarly, in IUPAC system, when ic of this ethanoic acid is replaced by acyl chloride, we get ethanoyl chloride. So these compounds in IUPAC system are named as alkanoyl chloride, and in common system by replacing the ic of the common name for the acid and then by adding the word chloride. Such as ethanoic acid, its IUPAC name will be ethanoyl chloride, that is a chloride which is obtained from it. Propanoic acid will give us propanoyl chloride. Butanoic acid, butanoyl chloride. So these are the formulas. OH is replaced by Cl and we get the corresponding acid chlorides, and they will be accordingly named. Now let us practice the name for some acid chlorides. Say this is a compound CH3CH2CH2COCl. It is a 4 carbon acid where OH has been replaced by Cl here. So it is a 4 carbon acid chloride. IUPAC name for a 4 carbon acid is butanoic acid, and its IUPAC name for the chloride will be IC is replaced by Acyl chloride, so it will become butanoyl chloride. And similarly, common name for this acid is N-butyric acid. So its name for the chloride will be N-butyryl chloride. Let us take another acid. This is 2-methyl propanoic acid, whose OH has been replaced by Cl. So its IUPAC name will be 2-methyl propanoyl chloride, and commonly this acid will be called as isobutyric acid. So its name for the chloride is isobutyryl chloride. This is the acid chloride from benzoic acid. The OH of the benzoic acid is displaced by Cl. So this is named as benzoyl chloride. Since the IUPAC name is also the same as well as the common name, so one name for this acid chloride, benzoyl chloride. Now this is a substituted benzoic acid, its acid chloride. So there is a nitro group at 4 position, so this is named as 4-nitrobenzoyl chloride. Then we can have acid chloride from those acids which have some cyclic saturated ring, like this is a 5-carbon ring cyclopentane to which COCl is attached. So this is named as cyclopentane carbonyl chloride, and if it is a 6-membered ring, then it is named as cyclohexane carbonyl chloride. Then we move on to the names for amides. These are amides where this is the NH2 group. In common system, ic acid is replaced by amide, whereas in IUPAC system, oic acid is replaced by amide. Let us take some example. This is a 1-carbon acid whose amide is here. So 1-carbon acid is named as methanoic acid, and this amide is named as methanamide. The common name for the acid is formic acid, and this amide is called formamide. Then there is a 2-carbon acid, ethanoic acid or acetic acid, and its amide is named as ethanamide or acetamide. A 3-carbon acid, its amide will be called as propanamide, and IUPAC name is propanamide. Common name will be propionamide, because commonly acid is known as propionic acid. So its common name for this amide is propionamide. Then these amides may not only have the simple NH2 group, because when they have simple NH2 group which has replaced OH, we call them as primary amides. But there are some other amines also can replace this OH, and when there is one alkyl group substituted, we call them as secondary amide. And if there are 2 alkyl groups substituting these 2 hydrogens of the primary amine, then we call them as tertiary amides. So amides are further classified as primary amides, secondary amides and tertiary amides. We have discussed the nomenclature for primary amides, where the OH is displaced by reaction with ammonia only. But if some other amine has displaced it, then they are secondary or tertiary amides are obtained, and they are named in that system. The alkyl group which is attached to the nitrogen, we write it before the name as N alkyl, and then we write the name of the amide. Such as this particular compound, it is a 2-carbon acid derivative, so it means it is ethanoic acid derivative. Then had it been NH2 only here, then we will call this compound as ethanamide. Now what has happened, one of the hydrogen of ethanamide is replaced by a methyl. So this methyl, since it is present on nitrogen, we will write as N-methyl, then ethanamide, because the system says whichever alkyl group is there on the nitrogen, we write its name first with a capital letter N and then the name of the amide. Let us take another example. This is the derivative of a 3-carbon acid. So means it is a propanamide derivative in which one of the hydrogen is substituted by ethyl group. So we call this as N-ethyl propanamide. These are the IUPAC names. In the common system, the same thing is applied. We will write the name of the alkyl group before the common name for that particular amide, such as we will call this as N-methyl acetamide, and we will call it as N-ethyl propionamide. Let us take some substituted amides. Say this is the simple primary amide propanamide. If one of the hydrogen is substituted by methyl, it is N-methyl propanamide. Suppose two hydrogens are displaced by these methyl groups, then it is named as N-dimethyl propanamide. This is one of the simple aromatic amide from benzoic acid named as benzamide. And if one of the hydrogen is substituted by a methyl group, this will be named as N-methyl benzamide. Suppose these are two different alkyl groups. One is a ethyl group, another is a methyl group. Then we will write the names for both the alkyl groups before the name of the amide. We will place one nitrogen before the name of each alkyl group, and these alkyl groups will be arranged alphabetically. So one is ethyl, another is methyl. So we will write as N-ethyl, N-methyl benzamide. Suppose there is a substituent in the ring. This is that benzamide which has one methyl group at the meta position. We will write this as 3-methyl benzamide, because in IUPAC system of aromatic compounds, the main functional group carbon is given the number 1 and then ring is numbered as 1, 2, 3. And in common system, this is amide from toluic acid, and methyl is at meta position, that acid is meta-toluic acid. So this is called as meta-toluamide. Then cyclic amides are also there, because there is a possibility that we may get amide from such an acid which has amino group substituted in the chain itself, and that amino group may combine with the same acid to give the amide like this. This can be a 1, 2, 3 carbon acid carrying an amino group which is cyclized here, a 4 carbon acid or a 5 carbon acid. These cyclic amides are called lactams, and then these lactams are named by placing the position of this nitrogen with the help of a Greek letter, and we call that carbon as alpha carbon to which the carboxyl group was attached, or now the carbonyl group is attached. So this is alpha carbon, this is beta carbon, this is gamma carbon, this is delta carbon. So this nitrogen is now attached to the delta carbon, and this 5 carbon acid 1, 2, 3, 4, 5, that name for the 5 carbon acid is valeric acid. This is the lactam obtained from 5 carbon acid, we call it as delta valerolactam. This is a 4 carbon acid, butyric acid, and this nitrogen is at alpha beta gamma position. So this is known as gamma butyrolactam. This is the alpha beta position on which this nitrogen is now there, and 3 carbon acid is propionic acid. So this is called as beta propiolactam. So cyclic amides are named in a slightly different way. We designate the position of nitrogen on the chain starting from the carbonyl site, and that carbon is assigned alpha to which carbonyl is attached, and the number of the carbon to which nitrogen is attached, that is mentioned, and then the ending term is lactam. Then very common compound you are familiar with is urea. In a way it is also amide because it has this CONH2 group. This urea is also named as carbamide. Actually it is the amide of another acid which is called carbamic acid, NH2COOH. This is acid, OH has been displaced by NH2. So we can say urea is the amide of carbamic acid, but carbamic acid itself is the amide of carbonic acid. Carbonic acid has got these 2 hydroxyl group. Actually carbonic acid is the solution of carbon dioxide in water, H2CO3. So the 2 hydroxyl groups, when they are displaced one by NH2 group, then we get urea. So urea is also considered as amide. Then the nomenclature of esters. Esters are the compounds in which OH has been displaced by another alcohol molecule, and for naming these compounds in common system as well as in IUPAC system, we first name this alkyl group that has come from alcohol, and then we name the acid part, and the ending ate is there, which replaces the ic acid of the acid part. So, let us take the example. Suppose this is the ester which is obtained from one carbon acid, which is methanoic acid. Then OH has been replaced by the alcohol methanol. So, alkyl group here is methyl. So, the nomenclature for this acid according to IUPAC system is methyl methanoate, because the IC acid of the acid part is to be displaced by ate. So, this is methyl methanoate. Commonly this acid is named as formic acid. So, common name for this compound is methyl formate. So, methyl methanoate and methyl formate. Let us take another compound. Now, this is a derivative from 2 carbon acid called ethanoic acid and commonly called acetic acid. Alcohol is again this methanol. So, alkyl group is methyl. So, IUPAC name for this compound is methyl ethanoate or methyl acetate. The next is we have this ethyl group and 1 carbon acid, that is methanoic acid. So, this will be named as ethyl methanoate or ethyl formate. Here we have this ethyl group and then 2 carbon acid, that is ethanoic acid. So, this compound will be named as ethyl ethanoate or ethyl acetate. We can have the esters from aromatic acids also. This is the ester from benzoic acid with methanol. So, this will be named as methyl benzoate. Common name also will be same, methyl benzoate. Now, we have to be very careful in naming the esters. When one of the part is aromatic, we have to see whether the aromatic part is from alcohol, that is alkyl part or aryl part on that side, or it is from acid. In this case, we find that acid is this part, is a 2 carbon acid, ethanoic acid, and here it is the phenol that has attached. So, this compound is named as phenyl ethanoate, or commonly named as phenyl acetate. Now, this is a 3 carbon acid, propanoic acid, and the alkyl group is ethyl. So, this is named as ethyl propanoate. Then esters can also be cyclic. Cyclic esters are obtained from those carboxylic acids which have hydroxyl group substituted on their chain, and when this hydroxyl group combines with the carboxyl group itself, we will get cyclic ester. The cyclic esters are named as lactones, and other rule for naming these esters remains the same, that we indicate the position of this hydroxyl group, that is the oxygen in the ester part, by a Greek letter alpha, beta or gamma, and alpha carbon is 1 to which carbon is attached. So, this is alpha beta, this is beta propiolactone, this is alpha beta gamma and 4 carbon acid, gamma beta-lactone, this is alpha beta gamma delta, and a 5 carbon acid called as delta valirolactone. Then the nomenclature of anhydrides. Anhydrides, as I said, are obtained when OH is replaced by another acid molecule. Now, what we can have, that the 2 acids which have formed an anhydride can be same or they can be different. So, first anhydrides are classified on this basis, that if R and R1 in the above formula, they are same, means this is the anhydride from same acids, we call such anhydrides as symmetrical anhydrides. And when these 2 alkyl groups or R groups are different, they are not identical, then these anhydrides are named as unsymmetrical anhydrides or mixed anhydrides. So, they are named in a slightly different way. In case of symmetrical anhydrides, we name the acid once, whereas in unsymmetrical or mixed anhydrides, the name of both the acids have to be placed there. Such as, let us name first some symmetrical anhydrides. This is the anhydride obtained from formic acid or methanoic acid. So, one acid molecule, a second acid molecule, they have eliminated water here. So, this anhydride is called methanoic anhydride or formic anhydride. Similarly, if we have an anhydride from acetic acid, the two molecules of acetic acid have combined. So, this will be named as ethanoic anhydride or acetic anhydride. This is a propanoic acid CH3CH2COH. So, this will be simply named as propanoic anhydride or propionic anhydride. Suppose we have the anhydride from benzoic acid, we will call it as benzoic anhydride. So, as long as the two acids which have formed the anhydride are identical, the name of the acid once and then word anhydride after that. But if the two acids are different, such as this is the anhydride of benzoic acid and ethanoic acid, in that case, as I said, we will name the two acids before the word anhydride, and these acids are named in alphabetical order. So, it is ethanoic E, this is benzoic B. So, this will be named as benzoic ethanoic anhydride. This is propanoic acid, this is ethanoic acid. Now, E comes first. So, this will be named as ethanoic propanoic anhydride. We can get anhydrides from dicarboxylic acids also. The carboxylic acid which have two carboxyl group in them, we have discussed such acids earlier, and this is the anhydride obtained from succinic acid, a 4 carbon acid 1, 2, 3, 4. So, this is simply called as succinic anhydride. Similarly, phthalic acid, where the two carboxyl group are attached to benzene ring at the ortho position, they can also form anhydride, and that anhydride will be named as phthalic anhydride. So, this is about the nomenclature part of these acid derivatives. Now, let us talk about their physical properties, and in physical properties let us first take up the state. Acid chlorides are mostly colorless liquids. These acid chlorides generally fume in air, and the reason for this is because they can easily be hydrolyzed. As the vapors of this acid chloride comes in air, gets hydrolyzed with the moisture in air, and what happens? HCl is formed and the fumes are obtained. Then lower acid anhydrides are also liquids. Formamide is the exception to all the amides that it is a liquid, and all other simple amides are solids. Then most of the esters are also liquids. Most of the esters, they have characteristic fruity smells. Then their solubility. These acid derivatives are mostly soluble in organic solvents. They dissolve in alcohol, acetone, chloroform, etc. In some solvent they will be less soluble, in some other solvent they will be more soluble, and these acid derivatives like esters and then some of the amides, they themselves are used as solvents. So, we talk about their solubility in water. The acid chlorides and acid anhydrides can't be said to dissolve in water because they react sometimes very violently with water and they get hydrolyzed. The hydrolysis reaction is like this. This is any acid chloride. This water attacks on the carbon, replaces the halogen. We will talk about this reaction in detail little later, and this Cl is replaced by OH part of the water, and then one H and one Cl, they go as HCl. So, acid chlorides and acid anhydrides cannot be dissolved in water because they get hydrolyzed. Some may hydrolyze at a very fast rate, some may hydrolyze at slow rate. Then the amides. The lower members of the amides are soluble in water, and generally they are soluble up to 5 or 6 carbon atoms. After that the solubility decreases, and this solubility of amides in water is due to the hydrogen bonding, because amides have this NH2 groups, these hydrogens, which can form hydrogen bond with water molecules, but as the size of this carbon chain will increase, it will become water repellent and their solubility decreases. Ester also are soluble in water, the esters of small size. The reason being same, because they can also form hydrogen bonding with water molecules, and generally up to 3 to 5 carbon esters are water soluble. After that solubility decreases drastically. Then their boiling point. Acid chlorides are polar molecules because they have carbon chlorine bond, whereas chlorine is electronegative, and they cannot form hydrogen bond amongst themselves. So, generally their boiling points are not very high, but definitely they are higher than alkanes because they have some dipole interactions, and their boiling points are generally lesser than the corresponding alcohols. Then ester molecules are also polar and cannot form hydrogen bond amongst each other. So, they also have a boiling point which are lower than the corresponding acids, very close to the corresponding acid chlorides. Then the amides have generally high boiling points, and again the reason being because they can form intermolecular hydrogen bonding. Amides have this NH, and these NH can form hydrogen bond with the carbonyl of another amide molecule. So, amides are generally high boiling liquids, that is why most of them are solids. This table gives some idea about the physical properties of compounds with comparable molecular mass. We have taken here a 4 carbon acid butanoic acid, then 4 carbon amide butanamide with the molecular mass very close to the acid 87, and its boiling point is higher, it is 216 to 220. The reason being that it can form more intermolecular hydrogen bonding. Then the isomer in which one of the methyl is attached to nitrogen and methyl propanamide, the boiling point is reduced. When it is N dimethyl propanamide, boiling point is reduced further to 166 degrees Celsius, because now there is no chances of intermolecular hydrogen bonding here. Similarly, when we have the corresponding esters or acid chlorides, they have lower boiling points because they cannot form any intermolecular hydrogen bonding. Then next we talk about the type of reactions these acid derivatives undergo. We call it as a nucleophilic acyl substitution. You see, this is the general formula for any acid derivative. This Y represents some group that has displaced OH. Due to the polar nature of this C double bond O, that is more electronegativity of oxygen, this carbonyl bond is polarized, this carbon has delta positive charge, and any nucleophile can attack this carbon. This attack of the nucleophile will be further enhanced if this Y group is also electronegative. And if we compare the halogen or alcoholic group OR or then OCOR in esters and NH2 in amides, they are all electronegative groups. So, due to their inductive effect caused due to higher electronegativity, the positive charge on this carbon is further enhanced, and when this positive charge is enhanced, nucleophiles can attack more easily. And if this Y group is such that it can undergo a resonance with this C double bond O, that is, it is a lone pair of electron which can involve themselves in resonance, then the strength of this CY bond would be increased and it will be difficult to break. So, the two effects are now opposing. If Y is more electronegative, positive charge will be more, and there are more chances that this group will be easily substituted. And if this Y group is involved in resonance, this CY bond becomes stronger, has got some double bond character, then it will be difficult to replace this Y plus. Any nucleophile which comes and attacks this carbon of the acid derivative and replaces this Y group, so that nucleophile will be attached to COR group, and this COR group is called acyl group. So, that is why these reactions are classified as nucleophilic acyl substitution reaction, means reaction is started with the help of a nucleophile. Overall, what has happened? One acyl group has attached to that nucleophilic group, and the reaction is substitution reaction. These nucleophilic acyl substitution reactions are shown by all acid derivatives, and the groups which are present can displace each other also. Like any Z that is a nucleophile, when it is going to attack one acid derivative, this pair of electron will move towards oxygen. Then in the next step, we have a carbon to which 4 groups are attached. One of them is oxygen electronegative, Y that is also an electronegative group, Z a nucleophile that has come is also electronegative. So, this is not a very stable entity, and it has a tendency to remove one of the group. so that we get sp2 hybridized carbon again as it was in the starting compound. So, the pair of electrons comes back, C double bond O is formed. If Y is displaced, Y is the group that was present in our starting molecule. So, we get the product in which Z has displaced Y. But if this Y is not a very good leaving group, that is, it is formed either a strong bond due to resonance or not a very strong base, then what may happen? This pair of electron comes back and Z leaves back and we get the starting compound. It means Z should be that group which can be able to displace this Y, should be able to form a stronger bond with this carbon, and Y should be a leaving group which can leave easily. So, a carboxylic acid derivative will undergo nucleophilic substitution provided the incoming group is a stronger base than the leaving group. So, leaving group will be that group which is a weaker base. Now, if we see this reaction on different acid derivatives themselves, so all the acid derivatives with esters, anhydrides, acid chlorides and amides are hydrolyzed to give corresponding carboxylic acid. Means if our nucleophile is water or hydroxide ion, then all these can be displaced, because hydroxide ion is a stronger nucleophile than all of these chloride or OR minus or OCOR minus or NH2 minus. So, it is able to displace all these groups, they all are hydrolyzed. When we talk about the stability or reactivity of different acid derivatives, we find that their reactivity increases towards the acid chloride, because a stronger base is a better nucleophile and weaker base is a better leaving group. So, for these groups we find that chloride or OCOR group or alkoxide or NH2 amide, their basicity increases. So, as the basicity increases, tendency to leave decreases. So, it is difficult to replace NH2 from an amide, but it is very easy to replace Cl from acid chloride. So, we can say that the reactivity of the acid derivatives increases in this order and their stability obviously will have the opposite order. So, stability increases in this order. So, amides are most stable and least reactive, acid chlorides are most reactive and least stable among them, and that is why the acid chlorides are used as a starting material for the synthesis of different acid derivatives. So, this chart shows that the acid chlorides can be converted into esters or amides, or can be hydrolyzed back to carboxylic acids, or can be converted to acid anhydrides. But amides can only be hydrolyzed to acids and cannot be converted back to any of these derivatives. So, this chart shows the sequence that which acid derivative can be obtained from which other acid derivative. Acid chloride, as I said, are the most reactive and least stable. They are used as intermediates for making other acid derivatives, such as ammonia can very easily react with acetyl chloride to give the compound acetamide. We will discuss this role of acid chlorides and the reactivity of other acid derivatives in our next session, where we will discuss their methods of preparation and some of their important chemical properties. So, today we have discussed that what are these acid derivatives, then we discussed the nomenclature of acid chlorides, amides, esters and acid anhydrides, that is how they are named according to IUPAC system as well as according to common system. We discussed briefly their physical properties, and then we have compared their reactivity, stability with respect to the nucleophilic reactions which they undergo. In the next class, we will talk about the preparation and properties of some of these acid derivatives. Thank you.